Good day everyone, my name is Alex Matthee. I'm a PhD candidate at the University of Twente, part of the EMC group. Today I'm going to be showing you about a demo PCB regarding a coax cable. Today we're going to be looking at a printed circuit board, uses a demo board showing a bad coaxial cable. Basically, we've got a trace running along the board, a very long configuration, and a return path coming on both sides of the trace on the way back. The trace is terminated with 50 ohms at the end, and basically we will be injecting a signal on UN on this side with a vector network analyzer. And what we will be measuring on the output port is the voltage across the ground traces, essentially. We'll be looking at the frequency range from 10 kilohertz to 100 megahertz. On this connection, we have essentially a short connection between the start input ground trace and just before the termination of the load resistor. This is essentially measuring the voltage across the start and the end of the ground trace conductor. Okay, for our setup today, we've got a vector network analyzer with two RF cables. This has been calibrated, and I'll connect the TX connection, which is measuring the S21 parameter on UN. And I'll take the RX connection and put that on the labeled short connector, which is essentially measuring the signal over the ground conductor. On the laptop, we can see the output of the VNA, which is from 10 kilohertz to 100 megahertz range. On the printed circuit board, we've got a signal trace surrounded by a return path. This is non-ideal. Essentially, for a perfect coax cable, we would want a signal trace to be completely surrounded, or any signal conductor to be completely surrounded by conducting material to shield it completely. In this case, we only have a return path trace on the left and the right side of the signal path. So when we inject a signal through the signal trace, we will have losses coming from this coax cable. Using the VNA, we'll be injecting a signal here at UN and measuring the potential difference at the end, between the end and the beginning of the signal return path. Because in this case the impedance is not zero, there'll be a potential difference across these 2 points, especially at higher frequencies. This can be caused by resistance, whether DC or skin depth, or even by inductance. This will be seen as a voltage difference across the return path represents energy loss from the system. This is energy radiated from the cable and can have an effect on nearby systems. Okay, looking at the signal trace of this measurement, you can see here there's a 0 dB reference and about 40 to 45 dB below it. The signal starts at about 10 kilohertz, and when you get to high frequencies, you can see a much smaller decibel reduction up until about 100 megahertz. So this is essentially due to inductance, where the larger amount of the signal frequency is emitted from the coax cable. So the same holds true for the reverse situation. If I take the two input cables and I reverse them, basically I've changed the two ports, and this now mimics an external signal coupling to this transmission line, which would essentially mean that it's some sort of system outside of this transmission line and it's interfering and coupling to this transmission line. Now if we do a frequency sweep from 10 kilohertz to 100 megahertz, similar to before, you see the exact same phenomenon. This effect is caused by transfer impedance. Transfer impedance is defined as the voltage over the load divided by the current induced on the return path or shield. This demo board is showing the signal lost from the transmission line, and by reversing the ports we show the energy coupled to the transmission line as it would be induced from an outside source. So in this case, transfer impedance is higher than ideal coaxial cable due to the guard traces next to the signal path compared to a completely shielded coaxial cable, and this causes higher induced voltages than would be induced on a ideal coaxial cable. So in case of a real coaxial cable, the induced or emitted signal energy would be much lower. Previously we looked at the transfer impedance of an example coax structure on a PCB. The transfer impedance on that PCB can be improved by adding a large ground plane or adding vias, for example, just anything to increase the electrical structure enclosing the signal conductor. So now for the next demo, we'll be looking at measurements of transfer impedance with a couple of cables, and we'll use the same setup with a VNA, a printed circuit board set up exactly for this experiment, and look at the results on the frequency plot from 10 kHz to 100 MHz. So for this experiment, I'll be using the VNA and injecting a signal which will be flowing through either one of these connectors, whichever I connect a cable to. This will basically be injecting a common mode current. The cable is then connected to the other side, in which a differential mode signal is measured. This will be shown on the screen. For the first cable, I'm using a standard coaxial cable, connecting it to the two BNC connectors. And the measuring point will be on this port. Okay, now here we have a relatively ideal coaxial cable, and looking at the frequency sweep of this, you can see the losses are quite low. Here is the 0 dB reference point, and it's compared to the previous cable, which was in relatively this region during this frequency area and moved up higher. This is much lower over a much wider frequency range because of the much lower transfer impedance on the cable due to its completely enclosed signal conductor. Okay, so now we saw the frequency sweep of a standard coaxial cable. I will remove this. And now we're taking a less ideal cable, which is simply two BNC connectors with two unshielded conductors. There will be a signal and a reference. Connecting this to the same connectors. Now if we look at the comparison, I'll run the frequency sweep again. So as you can see from the previous measurement, the transfer impedance is much lower on the more ideal coaxial cable compared to this just a dual conductor cable, which has a much higher transfer impedance measured across 10 kHz to 100 MHz. One interesting thing to note, since these cables are this one cable is two separate conductors, you can see if you move these conductors around, basically increasing the area of the loop between the two conductors would change the inductance of this cable. So this would also have an effect of the transfer impedance. So if I say move these two conductors apart, you can see a higher signal measured, and moving them very close to each other, you can see the transfer impedance measured is dropping significantly. So now I'm removing the previous cable that was measured, and I'll be connecting this cable, which is also two BNC connectors with a similar cable and a common mode choke. So since we are injecting a common mode current, the common mode chokes should essentially eliminate the common mode current flowing through the transmission line. So the blue trace you can see is, even though the cable is similar to the green trace, the common mode choke eliminates a significant portion of the common mode current, which is almost equal to the actual ideal coaxial cable, up until a certain point where the coil most likely saturate and the effect is lost in frequency above this band. So now I'll disconnect the cable, the standard cable, with the common mode choke. Now I'm connecting a cable with similar BNC connectors. It is a coaxial cable, but on the one section there is a loop area connected into the shield. Increasing this loop area between the conductors essentially increases the inductance of the transmission cable, and this will increase the transfer impedance. And now there's a few things we can do with this cable. I'm just going to run a continuous sweep and we can look at what the results are on the frequency plot. So the large loop area is a non-ideal. If I decrease this area by holding this close to the coaxial cable, this decreases the transfer impedance, as you can see by the violet plot. Increasing this loop area, once again the signal ratio increases, and actually by disconnecting this connector will produce an open circuit in the shield, which will essentially give you the highest transfer impedance possible with this transmission cable. And you can see this by the violet line that's moved up to one of the highest of all the measured cables. And closing it again, you can see that the transfer impedance once again drops. So essentially, modifying the area of this loop modifies the transfer impedance, and also of course creating an open circuit will give you the highest impedance manageable with this transmission cable. We've looked at a few different cable configurations and seen that the transfer impedance can vary widely due to the structure of the cable. A few things that can influence the transfer impedance of the cable includes resistance, whether it's DC resistance or skin effect. Also, loop structures in the cable itself can increase the inductance of the cable, which increases the impedance. And also the structure of the shielding. So if the structure of the conductive enclosure around the signal carrier also has a large effect on the transfer impedance. And essentially the higher transfer impedance increases the noise generated by the transmission cable itself, as well as increases susceptibility of the cable to noise from sources in the adjacent area. So essentially a lower transfer impedance is more desirable.